Absolutely. Absolutely. So first of all, good evening. It's Sophia from a frosty morning in Boulder, Colorado. We had about minus 20 centigrade this morning, so I'm happy my car started and I'm actually able to be with you and give you a presentation. And yeah, apologies for not actually being able to attend in person. Many thanks though for the organizers who's been really accommodating and helpful to make this remote presentation happen. So many thanks for that. I hope everybody can hear me well. That works out so far. And I think what I'm going to do, because I'm getting an audio feedback from the conference room. So while I'm actually working, as we're working our way through the slides, I might mute the conference room so we avoid the audio feedback. And then I unmute the conference room again for the discussion, so towards the end of the discussion. And for anybody else who's joining us remotely, any other remote participants, you are on mute by default as you join. So please use the comment section to raise a hand or initiate any type of discussion. And without further ado, I think we can get started. Let me see real quick if I can go to the muting part. I do see the participants here. And I'm going to mute you right now. All right. Just want to make sure that you can actually, can you confirm that you can see the slideshow? Slides in full screen? Okay. Okay, then I'm going to go and mute you real quick again. All right. Let's get started. So, again, many thanks for having me. Let's get started with my talk, Neon, from scientific strategy to long-term operation. And I'm going to focus on the slides here. So the spirit in which we're going to work through this is really to incorporate lessons learned through many collaborations that we had over the years with existing networks, Ameriflux, ICOS, LTI-Turn, to name a few, and then also having an open eye or be open to check whether there's whether Neon centralized approach lends itself to explore some novel systemic solutions. And we're going to see what I mean by that in a couple slides down the road. Now that said, we've been working on this for quite a while, together with you, together with the community. Now it's time to start to give back, and we'll see that we have our boots on the ground in the sense of we have quite a bit of equipment out there at this time. We're giving back starting to give back software, data, education resources, and so forth. And so with that spirit in mind, let's get started with a brief overview. Wide-reaching observational scales is going to be our first topic, which is also the motivation then for designing something like Neon, the National Ecological Observatory Network, for scaling, to specifically address scaling questions. We're going to talk about centralized data operations and monitoring, scalable scientific computing, and then ultimately, I think what's going to be really interesting, the prospect of combining ground-based, airborne and spaceborne data operationally in the future. And then I'm going to close with a brief summary and outlook. Let's get started here. Wide-reaching observational scales. Not so recently anymore, 2013, scaling was identified as one of the 100 fundamental ecological questions. So for example, how does spatial structure influence ecosystem function, and how do we integrate within and between spatial scales to assess function is one of the top priority questions that we can all contribute to. At the same time, the National Research Council was issuing a report that was saying, well, even if you want to go about that, our data still remains quite sparse spatially, or too sparse spatially, to test some of these mechanisms. And we really need to work on getting our hands on data with high spatial and temporal resolution. Then here's another commentary with regard to more coming from a carbon flux cycle that scaling down and scaling up are both critical for an integrated assessment of carbon cycling or carbon research, that the various spatial and temporal domains have the potential to constrain our understanding of carbon cycling and its budget. However, that we are really still lacking a good piece of ground-based data for validation purposes. Now, using that as motivation, we can see how we are able to go about that as a community, for example, through something like NEON. So we see here, and that has happened not just in a year, that has happened over more than a decade, is to figure out how such an observing system that's working from scales of micrometers to continents, how to go about designing such an observing system. So what we do see here is that we started, meaning we as the community at this point, started off with grand challenge questions, funneling them down, or grand challenge topics, funneling them down into addressable key questions, and then determining which kind of data products would actually be needed to address these key questions, which can then be produced with the observing systems at NEON, or how the observing systems are designed against, so that the data can then be disseminated to users who can actually go about addressing the key questions and do fundamental research with those. Now, here an overview of this multi-scale NEON observing system that really goes from micrometers to continents in terms of spatial scales, and at the same time from milliseconds to decades in time. So the entire observing system is designed to run for 3 decades. Now, if that doesn't sound like a fairy tale, let's see how this fairy tale is shaping up these days. So essentially, what the NEON fairy tale would look like, something like this. We have a tower and people constantly in the field, people wading through streams, taking samples, and remote sensing being there 24/7. Now, here's how reality looks like. We do have quite a number of our towers phased into operations at this point. It's a total of 47 terrestrial towers measuring ecosystem fluxes. There's also a lot of other instrumentation in the field, as you can see here, soil arrays, in fact, stream measurements, buoys on lakes, and so forth. So there's indeed quite a bandwidth of observations that can be used together, which is a great data foundation, great database to work with, but it's also a challenge to maintain and a challenge to make sense out of. And so this was not only the terrestrial infrastructure. In addition to the terrestrial infrastructure, there's actually indeed people sampling in the field, sampling plants, biomass, litter, but also mammals and insects, doing regular soil coring. And we do have an airborne platform as well that visits our sites once to twice a year. So to summarize, overall, we're measuring over 24 states in the US with about 81 field sites and close to 200 data products that are coming online as we're speaking. And just give me a second here to take a sip. I'm going to unmute real quick just to see whether everybody can still hear me well and the presentation is going well. Pavel, can you confirm? Okay, great, awesome. Just one second. All right, I'll put you on mute again, and let's keep going. So then the whole observatory is organized strategically in 20 what we call eco-climatological domains. So what that means is essentially that over a decade, people have been trying to identify how many sites do we actually need to to explain sufficient amount of variation, sufficient meaning that we don't get to an area where each additional site is only explaining a small fraction of additional environmental behavior. And so there were clustering analysis done here, in this case, Hargrove and Hoffman, that informed the observatory design, which ended up being, so this critical threshold here being 20 domains, each with roughly 2 to 3 infrastructure sites, terrestrial infrastructure sites, and each domain office as well, with people that go in the field, maintain this instrumentation, and perform the sampling routes. This is kind of a unique approach to ecosystem research in a sense that in the past we've really been seeing much more grassroots and bottom-up development. It's really important to understand specifics at a site and very, very specific research questions with regard to individual biome and ecosystem. The difference here is that the focus of the observatory is really the continent or continental scale ecology. And through this kind of design, we already see first gain. So we're working closely with Ameriflux, for example, and when we are drawing the various sites, Ameriflux sites and NEON sites, over the same map with ecosystems, we see, hey, we already gained something here. There's an ecoclimate that is not previously covered in a continuous fashion. So we can actually begin to add to our foundation of ecological information. And this is a neat outcome, a neat first research outcome here as well with regard to the observatory strategy. Maheka et al. What they published is has a focus on researching extreme events. And what they find is that looking at the median extreme event with about 130 Ameriflux sites, our detection capability for understanding and capturing those events is about 40 to 50%. And with only a third of the NEON sites, we still get about 2/3 the detection rate, which can be related to the strategic design. So we're looking forward for a lot of synergies to be had among these networks. Okay, 1 second. So with this, we face a challenge in data operations in monitoring. I'm briefly going to talk about how we're tackling this and what kind of measures and processes we are bringing in place to operate the observatory. So what you see here is the general data operations architecture. We don't need to go into any details. In general, what you see here is that any type of observations in the field happen on the left-hand side. They are being ingested towards the center into a public data repository. Then all types of what we call transitions or calculations are happening on this raw data. And then the data is being provided through what's called the Golden Gate to a publicly accessible data portal. And there's only 2 areas really that I want to dive in a little bit deeper. And the first one of which is the science operations management, which is this component here, as you can see, located very well at the center of it all. So what that means is, if one wants to operate a behemoth like that, we really need to think about problem tracking resolution along the entire chain, which starts with training, over preventative maintenance, sensor calibration, health status monitoring, the actual data processing, but then also continuously monitoring data quality and eventually data revisioning. And so my colleague Korb Sturtevant has been diligently working out to bring in place such a system with many other colleagues. And one of the unique features that we already see, but just want to briefly demonstrate here, allows us to essentially convolve information from the site. So observations such as, hey, we actually have a bird's nest in our rain collector, so you might not want to use this data or at least publish it with a quality flag that says, be careful, you probably don't want to use this as a data consummate. And all of this is integrated through a maintenance app here, where people can go with a handheld device in the field, and these trouble tickets are, at least we're in the process of automating that, that it comes in and it's then automatically being included in the data processing chain. What then that whole SOM, Science Operation Management, leads to is essentially a top-down view of, hey, how are we doing? Here, in the case of data completeness, data validity, as you see, it's still work in progress, but we're getting there. And then you can drill down if something is not working as expected at several sites or with several data products. The intention is to really be able to drill down to, if necessary, a job review in infrared gas analyzer tells us, oh crap, I issue a quality flag and please change me out. So the next time that a person, the field personnel goes to the site, this person would be informed, please bring a new infrared gas analyzer and install that to maximize data coverage. So eventually, what all of that leads to is data products and data access. So it goes beyond the flux data, where I'm really focusing with this talk. We have a lot of remote sensing people, proximate sensing people in the audience. So I wanted to show a couple of other, visually show a couple of other data products. All of these, regardless of type of data product, are available from the NEON data portal, as well as through an API. And there's already tools for several programming languages where you can directly access the portal from your code base. We don't stop there, so the data is not just going out through the data portal, but we also continue to work with a lot of networks around us. And this is not actually a pilot project anymore. We're working at this point really closely with Ameriflux. We have 9 of our 47 sites registered at this time and are getting ready to submit data, which we see here. This one example, super site that we registered. And we also do, for example, work together with Ameriflux and utilize the Ameriflux pipeline to do some of the gap filling. It would be it's unnecessary to reinvent the wheel in terms of gap filling in this case. Rather than that, we join forces, use whatever gap filling algorithms are already available, harness those, and improve those together where possible. We also, going beyond mere data processing on the back end, so the downstream part, there's also an upstream part that we realize with regard to the airborne payloads that visit NEON sites. There's also quite a few Ameriflux sites in the vicinity, either co-located or adjacent. And so we're beginning to figure out which are those sites, and can we work together with the Ameriflux PIs on the ground to let them know and coordinate with them, hey, NEON is planning to fly. Do we want to make sure that your site is covered from the NEON side? At the same time, do you want to make sure that your equipment is actually running and is fully calibrated on the ground? Now, in order to be able to use these resources, such as data products, we're also going to look at software later. But in order to be able to use this and have tutorials, there are educational resources as well from NEON. As you see here, for example, a snippet from a video that explains what is eddy covariance, what kind of assumption does it make, how do we measure it in the field, and what are the outcomes actually useful for. And there's many more of these kind of videos. So if you're interested, or if you're seeking help or guidance with how to use eddy covariance NEON data products or other tools, then this is a great resource. With that, we're paving the way to talk about scalable scientific computing. And that is the second part with regard to the overall data operations architecture that I'd like to briefly point out or show. So this is the bottom right part here, where it says eddy covariance R code, which is essentially an extension that is plugged into the overall operations architecture that can be modularly plugged in. I see that somebody's, oh no, audio should still be all right, good. So what that is, what's happening in that area is that we have, together with about, at this point, probably 10, 20 contributors globally been coding up several R packages called EDI4R that allow processing raw data, EDI4R's raw data, 20 to 40 hertz data, 2.5 hours. And some of these are already publicly available. More of them are becoming publicly available. And they are packaged together with other R packages such as ENIO Scanner. Some of us might have heard of NPI's RD-Proc R packages to really provide an end-to-end analytics framework, and including extensible workflow. So there's examples in there, and one can essentially plug in one's own data and extend on what's already in there without having to swap among multiple or clutch together multiple different environments via different inputs and outputs. And the way that it's distributed here and how we want to intend to ensure community access and extensibility is what is called a Docker shipper containing system. So essentially what happens is all these things I was just talking about, these packages and libraries are compiled in one of those containers, which is like a really slim virtual machine that anybody can download from the web and apply to their own, and apply the contents therein and the workflows and the software to their own data in a bitwise identical way. So we really ensure that this is happening in a very traceable fashion. And what that then enables is what we call the development and operations framework with the science community at its center. So science recipes, we're all publishing papers, which are essentially recipes how to go about extracting information from and collating information from the environment, using these recipes to funnel them down into code, and Neon Science is more than happy to help with that via a public GitHub repository, which is then packaged, accessible for all of us in Docker containers that can be deployed to create the data products of your desire and getting closer to what's really useful, as well as to all of us on our own laptops or clusters or for our own research purposes. And here's just a quick comparison with other software that's used quite a bit in the community. In this case, it's EDI-Pro. So we've been processing the same data with EDI-Pro and EDI4R, and we see we have essentially identical results, with the difference that EDI4R allows you to modularly adjust any part of the processing chain, and if you decide so, really go to the individual lines of code. The characteristics of the resulting pipeline is near real-time processing. So data that's being collected at site is accessible or intended to be accessible eventually a week to a month after it's being collected. And the whole approach is extensible, meaning something we would like to work towards together with you is operational data fusion across these various data products or across these various observations that we've been looking at initially. And with that, we're leading into the part combining ground-based, airborne, and spaceborne data, which is not currently happening at NEON, but as I just mentioned, that's something that would be really great to work towards as a community, to do this operationally and provide really useful data products. Now, the scope of the task here is really that from our various platforms and observations that we have, we get in a space-time type diagram, we get very versatile, very different spatial and temporal coverage from different platforms, as well as resolution. And some of these areas, some of these space-time domains, mostly the coarser ones, they are already being integrated quite well in things like Earth system models. But then there's also an area towards the finer spatial scales, space and time scales at which many of the ecological processes are rooted, or environmental processes are rooted, that we still ask for improved model data fusion. And one of these areas, or one of the ways how to go about this is here what we call the environmental response function. So essentially what that is doing is it acknowledges that our various observations have different source area or are representing different things. If we're doing an optical measurement then we can potentially nicely georeference that, as we see here on the ground. If we do our atmospheric measurement, we have plume dispersion going on. And if we do an atmospheric measurement at different levels, or we measure fluxes or scalars, they all have different source areas. And so what this method is intending to do is to essentially intersect the space-time changing source areas of meteorological observations with those more fixed space-time areas of remote sensing observations. And this is done with time frequency decomposition and footprint modeling and all kind of these interesting things, so that it allows us to extract response relationships between our various observations. And we can then use these response relationships, for example, to address things like, or better resolve terms in a continuity equation here in this case for eddy covariance, but continuity equation is invoked in many types of measurement systems or analytics derivations that we intend to do, that we intend to infer information from the environment. This again is an example for storage exchange from eddy covariance system, and what it yields with that is essentially previously we had many disparate individual data points, whereas now this really creates an information continuum where over a target area, such as a remote sensing grid, say 10 by 10, or in this case 20 by 20 kilometer, we get a probability density function of the target quantity, such as here storage flux. And here an example of how that looks like in reality using this kind of remote sensing and flux and meteorological data. Here on the left-hand side, we see the time slices, how the storage flux evolves. On the right-hand side, we do see how the turbulent flux evolves over time. And what is shown here in these little boxes is essentially what could be, for example, the cell of an Earth system model. And we see how the source area, the footprint of the flux measurement, dances around across these cells, and would really be hard without acknowledging that this source area changes to infer robust relationships between these type of disparate observations. So again, in this example application for eddy covariance fluxes, what this allows us to do is over target domain, such as it can be a MODIS grid cell or it can be an Earth system model grid cell, to really come up with robust estimates and probability density functions, so defensible results with uncertainty estimate that share the same space-time domain as whatever target application is. And application examples are, these things are real-time capable, so it's possible, or would be possible in the future, to work towards including that into some of the data processing chains. As we've been talking about, I've been talking from the NEON perspective, but also NASA EcoStress has been soliciting proposals to look into these kind of developments. And with that, I get to the summary and outlook part. So to conclude, bridging scales is one of the fundamental challenges in ecology, and NEON is designed to address this challenge. We attempt to centralize data operations to efficiently manage data quality and standardization. And in result, what's available from the data portal and in extension, other network portals are coordinated and interoperable NEON Flux in situ proximal remote sensing data products. Not only the data products, but also the software to derive these data products are available public and are becoming more and more available public and online. And what we would like to work towards in the near future is to combine data across scales operationally with things like environmental response functions. So joint proposal writing, for example, could be really interesting, and I'd like to point out here such a case where this is currently happening. So there's been a gap being identified with regard to our airborne remote sensing capabilities, specifically with regards to rapid deployments, such as we call it here target opportunity measurement campaigns for extreme ecological events. And along those same lines, proposal writing with regard to operational data fusion, that would be something that we'd be really excited about. And with that, I conclude, and I am unmuting the meeting room again, and I'm happy to take any questions. Sorry, if there was a question, then I guess I didn't hear it. Could somebody repeat that closer to the microphone?
Microphone is now so close that it can't be close.
Oh, you actually, there is a microphone.
Okay, so the Timo Vetala from in ICOS, there are for some most important measurements the idea that there should be spare instruments on the cell readily available if the instrument gets broken. This idea is quite ideal. Works so well in practice, at least not yet. How is the spirit in NEON? Do you also have some kind of demand for a spare instrument? Do you avoid really the gaps in the system? What is your policy?
Yeah. So if I understand that correctly, I just want to repeat the question so I make sure I actually answer the question or something else. If I understand correctly, the question is, what about when sensors break or need to be exchanged in the field? Are there backup instruments?
Yes.
Okay. Yes. Yeah. So yes, there are backup instruments. I think roughly on the order of 30% additional instrumentation, or in some cases where we're thinking that, for example, instrumentation with the same firmware or the same hardware characteristics of that same model will be discontinued soon. Even more than 1/3 of additional instruments have been acquired. And what's happening with these instruments, they're routinely being calibrated here at NEON headquarters in Boulder, Colorado. And they are essentially rotating in and out of the field sites every year for the majority of these instruments. And if at the same time an instrument breaks between these 1 year routine intervals, then this is being swapped out as well based on the spares that are waiting here in Boulder, Colorado.
Is there any questions? I'll have one quick question. Would you actually to Stefan that called that different materials and icons that could be some initiatives that a certain extent to do similar things? And what is the level of communication between you guys that is possible?
I can answer first. So I know that it is really overlapping. In ICOS and NEON is really from the factors and related ecophysiology and society. So I know that the ecosystem semantics and Dario Papale, Dennis or the head team, they are, especially Dario, communicating very much with NEON. So, and related to protocols and data processing. So I don't know personally really the details, but there is my understanding of discussion.
Stefan, would you like to ask something or you're fine?
he's fine. I've never seen any.
I do have a bit of a trouble picking up the voice, or clearly picking up the voices. Sorry, was there another question for me?
Yeah, I mean, I had a question, but I think Timo has always provided the answer. The level of exchange of information between NEON and ICOS, which you are doing.
Okay.
Yeah, but Timo answered, so I think we are fine here.
Yeah. So I think several years ago, also when ICOS was beginning to think about what's being called protocols in ICOS. So essentially, how is information being derived from observations in the field? We've been, at that point, I think it was in Lyon, when was that, maybe 4 or 5 years ago. From that point on, we've been sticking our heads together. We've been mutually involved in our working groups. So NEON personnel on ICOS working groups and vice versa. So there are some differences still in terms of how we go about data processing, but that's kind of trying to cater to some of the unique aspects of the networks, in the sense that NEON is really fully centralized, which has its upsides and downsides. But in that way, we can harness some of what we called, what I was earlier referring to, systemic solutions, where things like that are still a bit potentially harder, or need to be, there needs to be more consideration with individual PIs and individual member country funding and so forth in Europe. And as a result of that, there are several differences, but at the same time, we intend to share the same post-processing and post-harmonization of specifically the Flux data products, which really intends to ensure that our networks are not biased against each other, and that we're all able to use these data products together.
Okay. And the last thing, like, some of the guys from the Spectra community, like, could you advertise like a department or section or whatsoever within NEON, which is dealing specifically with spectral data?
Sorry, I didn't quite understand that. It's about advertising something in the abstract and with data?
No, I was just asking whether you can quickly advertise a department, unit, or section within dedicated specifically to remote or proximal sensing.
Okay, I think I'm actually hearing you still through the computer microphone, so this was already much better. I think you got closer to the computer.
Yeah.
Okay, so Carolina, were you asking about any specific applications with regards, for example, Flux data, with regard to proximal and remote sensing, how these can be used together?
No, I was asking to advertise a unit, a department, or whatsoever within NEON, which is working with proximal or remote sensing data, so the guys here, present here, can have a reference.
I see. Now I hear you very clearly. That's awesome. Okay, yes. So it's called NEON AOP, and I'm more than happy. So if you look up, or you could just Google NEON AOP, you'll find that online, and we have our own webpage for them. They do use a lot of proximal sensing to calibrate their remote sensing data, which they fly, the sensors they fly on the big twin otters. So that's the department really to go to. Airborne Observation, NEON Airborne Observation Platform, or in short, NEON AOP.